Hi everyone. I am going to cover slides 1 through 10 for this video. So the first page, all you needed to do is say how you feel and draw a picture. So I'll go through to the next slide. We have how are factors related to zeros? Last week we saw that factors in our polynomials correspond to x-intercepts on the graph. And they give us an example. Number 1, it says f of x, which we all know is the same as y, is equal to x minus 1 times x minus 2 times x minus 3 times x minus 4 times x minus 5. And then you are asked to complete this table here. So if you recall in the table, we have listed our x's, so that is our input. They're basically saying when x is 1, what is f of x? So f of x is when we plug in 1 into this equation. If I plugged in 1 into x, 1 minus 1 would be 0. And then 0 times any number we know is also 0. One way you can write this is f of 1 is equal to 0. When x is 1, plug in 1, y will equal 0. And then the second row says what happens when x is 2. Well, if I plug in 2 into the first one, 2 minus 1 is 1. But then once I get to the second factor, 2 minus 2 is 0. And once I have a 0 in one of the factors, we know that 0 times any number is 0. So that means that f of 2 is equal to 0 as well. And can you see the pattern? I also have 3. If I plug in 3 into the third one, I will get 0. And if I plug in 4 to the fourth one, that will make it 0. And so it doesn't matter what it is in the other factors because we know that 0 times any number is 0. So for the next one, you would just say f of 3 equals 0. And by the way, if you only wrote 0 here, that is correct too. But I'm just putting that extra notation to show you that f of 3 equals 0 is one way to represent this. And we have f of 5. In the last factor, we can see that will equal 0 as well. Let me change this one also to f of 4 equal to 0. Okay. Question number 2, it says in the box below, write an equation that satisfies f of 10 equals 0, f of minus 3 equals 0, f of 25 equals 0. So basically, if we look at the column that I just filled in, now they're saying, what if you had an equation with when x equals 10 or when x equals negative 3, what is y? So what do you think? If you recall, just a little side note, we have done this before in last semester, looking at the differences between factors and x-intercepts. So here's a simple quadratic equation that is in factored form. If we wanted to find our zeros, we know that we can use the zero product property and find our zeros. So what is a zero product property? It's basically when we take every factor, so this right here is a factor, so this is one factor. Remember what a factor is. Any number that multiplies another number is a factor. So here is our other factor. And if we take our two factors and set each one equal to 0, x plus 2 equals 0, we subtract 2 on both sides, and we get that x equals negative 2. So if you recall how we go from a factor and then backwards to an x-intercept, we're basically, oh my goodness, I'm trying to use this eraser at the same time as I'm using this pen, and so it just erased it. All right, so x equals -2. So our factor was x plus 2, as you can see here. And using the zero product property, we found that our x-intercepts was x equal -2. Remember, an x-intercept is when y equals 0. So when y equals 0, we have x is equal to -2. And using the same idea here, we can see, using the zero product property, that x minus 3 equals 0. So therefore, x equals 3. So we have two intercepts. So our factors, if we listed that, one factor would be x plus 2, and our other factor is x minus 3. Now this is just a quadratic, so I could have many factors, not just two. So if we go back to this, you could see number 1 has listed 5 factors, 1, 2, 3, 4, 5. So we will have 5 intercepts. Now in this case, if we went backwards and we wanted to write an equation, well, going backwards, we know that if x equals 10, that means a factor is x minus 10. And if x here equals -3, we know a factor is x plus 3. And if x equals 25, then we know a factor is x minus 25. So writing this down as an equation, you probably already guessed it. And if you said x, or not guessed it, but wrote this down. So x minus 10 is the first one. X plus 3 is the second one. And the next one would be x minus 25. Okay, explain your thinking. All right, so here you can pretty much restate what I mentioned. So anytime you have factors, then using the zero product property right here, we can get our x-intercepts. So go ahead and explain that in some way here. All right, what's next? So for this example, we are given a parabola, and it says match the graph parabola by writing its equation below in factored form. So we can see we have an x-intercept at -2, 0, and an x-intercept at 6, 0. So recall, there's many ways to represent writing an intercept. One way is to write it as an ordered pair. Okay, so if I wanted to write an equation here, we can write x plus 2. You see, x plus 2 on its own is just a line, and then times x minus 6. And there you go, the graph matches. Yay, we did it. Here it says, here's what we will call a pass. When the graph goes smoothly x-axis without changing direction, we call that a pass. Notice that at x equals -2 and x equals 6, the graph gets the x-axis, it simply passes through. This is also known as a unique root. So let's go ahead and see where that is. So the graph here passes through the point -2, 0, and it also passes through the point 6, 0. So if we were to write this in factored form, we can see that the exponent, the 1 here, we don't really need that. It is understood that if you see below, it is not written in, we also can write it in, and we would get the exact same equation. So always remember those invisible ones. In the box below, write another equation that would have a pass. So here you can basically write any equation you would like where you would create a graph that passes. So in other words, you can create any x-intercepts that you would like. So for example, you can write whatever you like. The answers here can vary from student to student. If you wrote x minus 5 times x plus 3, for example, that would be perfectly fine. And this would only pass the graph it would pass at 5 comma 0, and then it would also pass through negative 3 comma 0. All right, match the graph by writing the equation of the parabola below. Okay, so let's look at the parabola. It has, this time, if you could see, there's an intercept at 6 comma 0, but we would not call this a pass because it's not passing through, it's not passing the x-axis, it's just touching it and then it changes direction. So this is what we call a bounce. And I believe we saw this in the first activity, the first Desmos activity. So it says match the graph by writing the equation. So if you recall, a bounce means that the degree is 2, which means we have a double root at the point 6 comma 0. What does a double root mean? It means that if we were to graph it, we actually have an x-intercept, two double points at 6 comma 0. So this could look something like x minus 6, and that right now has degree 1, which only shows me a line. So to raise it, you need to do the little hat above the 6 and put a 2, and that will square it. So there's my bounce. Now recall, x minus 6 squared is the same thing as if you wrote it in factored form. It just means x minus 6 times x minus 6. So either way will work. You can write it in both ways. When the graph hits the x-axis and quickly changes direction without crossing the x-axis, we're going to call this a bounce. So this happens when you have an even exponent. So right now we're only looking at degree 2 for bounces, but this just means even, that it could be a degree 4, a degree 6. Anything with an even degree will bounce off the graph. So let's take a look. So the equation for the graph has a root at 6. That means it will bounce at x equals 6. In the box below, write another equation that would have a bounce. Okay, so in this case, you can write any equation you like, again, as long as the degree is even. In this case, we are looking at degrees 2 mainly, so I could put x plus 3 squared. That would have a bounce. But if you put x plus 3, 22, that would also be an even number, so it would also bounce. Okay, let's see what is next. All right, so what we have here is a snake-like graph. So if you recall from last semester, a snake-like graph was a cubic function that we learned. So let's see where the graph here crosses the x-axis, and it does cross through, so we call that a pass at the point 1 comma 0, and then there is a bounce at 4 comma 0. So if you try to write this, then you could basically write down the equation as x minus 1. You could see it crosses through the point 1 here. So that we want to keep that as degree 1, but then it's going to bounce at 4. So then it also bounces through 4. If you left it like this, you could see that what we created was a parabola, and it does cross our intercept, but it doesn't match our graph. So where it bounces right here, you would need to raise it to the second power. And there we go, our graph matches. Now, the order in which you write your factors doesn't matter. Okay, so for this slide, we are asked to determine the equation of the blue parabola by adjusting the value of the a. All right, so you could see that the points both have intercept at -4, 0 and also an intercept at 9, 0. So we want to move, if you can see the a value is not given, we want to move this slider to see where we could match the graph. So as I'm moving to the right, the graph is getting steeper, as you can see. And as I'm moving to the left, my slider to the left, the numbers are getting smaller and my graph is getting wider. So it looks like I should be moving it to the right. And I'm going to stop as soon as it touches the graph. And I believe it is here, 3.5. Okay, so our a value right here, if I changed it to 3.5, matches the graph. Okay. Find the equation of the blue parabola by changing the value of a. All right, so right now, if you can see, I have x plus 5. So the same idea, we're going to have to play around with the a value. Do you guys remember what happens to a graph when it is flipped? Because you could see the red graph is facing up and the blue graph is facing down. So what happens when the graph flips? Well, let's take a look. If I move my slider and I'm moving it to the right, it's just going to make it steeper. But if I move it to the left and then go below 0, in other words, negative, I can match the a value. So it looks like it is at -2. So our a value is at -2. And this will complete slides 1 through 10, and I will, the next slides will be 11 through 20.